Hello, everyone. Can you guys hear me?
Yeah, we can hear you.
And you guys can see the screen of
Yeah,
the my
as
slides.
well. Yeah.
Okay, cool. Thanks so much for the nice introduction from the host. My name is Zuoyi. I'm currently a master student in HCI lab at the Computer Science Department in the University of Manitoba. Today, I'm going to talk about my paper, a smart utensil for detecting food pickup gesture and amount while eating. Oh, sorry. Uh, my paper was conducted with my lab members, Zhang, Zuoyi, Rappel, Kenny Hong, and previous lab member Dr. Chen Han, now associate professor in Chinese Academy of Science, and the research associate in our lab, Dr. Yumiko Sakamoto. The paper is supervised by my advisor, Dr. Prem Irani. So let's get started. Imagine you are having breakfast and you look at your watch and find you have to finish your meal and catch up the bus. Your family members saying hurry up to you. Yes, we all have such experience to quickly finish a meal. However, I'm wondering, have you ever thought about how does such fast eating behavior mean to your health? Researchers have found high eating speed could lead to serious health problems, such as elevated risk of obesity and increased risk of erosive gastritis. In contrast, studies show that a reduced eating rate is associated with a reduction of energy intake, and so that it could minimize the risk of obesity. Slower eating rate could also help individuals have earlier satiety. Reducing eating rates is one of the fundamental principles of mindful eating. Thus, we know that having good eating habits, especially an appropriate eating rate, is important. So, how could we help faster eaters to reduce their eating rate? To regulate the eating rate, numerous solutions have been created. The solutions must first detect the eating rate, such as eating gesture and the food weight. Then the solution could influence the eating rate by providing various interventions, such as manipulated eating rate by changing food delivery speed in previous studies or vibration on smart devices. You may see the vibration in the animation of this 10S fork. However, the 10S fork device cannot detect the food weight. There are devices that used to detect the eating rate. For example, a mandometer in the left picture, you can see that the users put a scale-based device uh, under the plate of the food, and a smartphone application will showing how much food user have eat and how much food left in plate to get the eating speed. Another device is a smart plate in the right figure. The users are asked to put the food on the plate, and the device could sense the weight on it. Uh, then the users are asked to take a picture of the food to help the system to classify the type of food and calculate the calorie of it. However, such a tool is kind of burdensome and discourage the use of them. In this project, we want to design self-contained devices that are easy to carry and use in every dining places without extra devices. More important, the device could detect the eating rate accurately. To, To explore the solution on the eating rate detection, we conducted a literature review on the technique of the eating detection. The first categories of the related work fall into the eating detection techniques. We found the researchers leveraged the inertial measurement sensor attached on the smartwatch or wristband to detect the eating moment and eating um, motion. To detect the eating gesture and bite, previous researcher leveraged the AMU sensor on the wristband to detect the movement of each bite. Uh, uh, there's one previous project to leverage machine learning. There's a couple of previous projects also leverage machine learning algorithm to train models based on the MU sensor data. However, the model trained is a bit large and hard to put and a little bit hard to put into the embedded device developed by us in this project. As for the food weight detection, previous researchers applied chewing sound to predict the weight of each bite through linear regression. One previous project also applied in-ear audio sensor and motion sensor on wristband to estimate the food amount in weight through linear regression. Uh, one previous researchers leveraged the AMU sensor on the smartwatch to predict the fluid weight drank by the participant in their studies. After the literature search, we conducted the prototype design and developed a folk prototype to collect sensor data and proposed a solution to detect food pickup gesture and estimate the food weight on the folk. We also conducted a data collection study with participants to evaluate our solution. Here, we propose the development of a smart fork prototype, which is easy to carry, and the fork can calculate data from the MU and the load cell sensors on it. Then the data could be used to help us to develop and evaluate the solution. As I mentioned, we developed a solution on the detection part. We leverage the MU sensor data to detect the food pickup gesture and leverage the load cell sensor data to predict the weight on the food of the food on the fork based on a linear regression algorithm. Our prototype of the smart fork utensil is shown in this picture. It's a self-contained device with a controller section for the data collection. The current prototype contains a PCB board with a microcontroller on it, a Bluetooth module was embedded in it to support data transmission. A load cell sensor and was attached with its corresponding driver to extract the load cell sensor data. There's an MU sensor on the board also. Finally, the prototype is powered by a battery to make it a self-contained device. We first investigate the user's eating gesture. We found there is a rotational movement while eating using a fork. You can see that when the user pick up food and then angling the fork to deliver it to the mouth. Here we compute the raw velocity to detect the rotational gesture. You can see a clear repetitive pattern on the raw velocity data from participant 1 in our study. We developed a threshold value-based algorithm. and we focused on food pickup gesture. We so that we could infer the bias on the food pickup gesture. This picture shows each cycle of the food pickup detection. Here, each cycle started from the low velocity higher than threshold value 1, and then the low velocity will pass the threshold value 2. The cycle will end at the low velocity higher than the third threshold value. Then the next cycle of the detection will start and repeat this process again. We leverage linear regression to estimate the food weight on the folk during eating in motion. We compute the average of the load cell values and applied a linear regression to compute the weight. The formula is here. W is estimated weight, and LC is average load cell data. P and I are regression parameters. Here we had one assumption that the left-hand user will have same rotational movement, and since we didn't find left-hand users in our study, we would investigate the left-hand issue in the future work. We didn't apply smoothing technique and filter to the raw data since we found that the noise is in a controlled range. The preliminary study shows that the noise will not affect the results significantly. 12 participants, including 3 males, were recruited for our study from a local university. Data from 2 participants were excluded due to the mechanical issues. Thus, for analysis, we used the remaining 10 participants, including 2 female from this study. All participants were right-handed. The study were conducted in our lab. 2 types of fruit cup were provided in showing in the picture. First, the instruction of the study were provided by the researcher to the participants. Then the participants were asked to eat at their normal eating speed. The prototype fork was put horizontally facing upward to initialize the load cell and AMD sensor before the participant starts to use it and starts the eating session. Each participant were asked to use the prototype, which would send real-time data to the computer via Bluetooth. During each session, we use a scale under the bowl of the fruit to track the weight in the bowl, and a GoPro camera was placed in front of the participant to capture the ground truth of the eating gesture and the food weight showing on the scale screen. We asked the participant to perform a high or a quick vertical movements with the fork at the beginning and the end of the session to generate a high peak in the data to support the synchronization of the sensor data and the ground truth. After the study, we use Boho software to annotate the video for the ground truth data of the gesture and the weight. We then plot the raw data at the axis of the acceleration in MU. We found the high peak gesture in the plot, and then we found the corresponding data point in the sensor data. Thus, we could synchronize the moment of the moment of the high peak movement in the video with the corresponding data point in the data set. We applied our algorithm to perform the gesture detection and compute the sensitivity of the food pickup detection. We first calculate the number of the true detection, undetected gesture, and false detection. True detection are pickup gestures that are within the circle of the pickup gesture detected, defined by the according to the algorithm. Additional pickup within the same cycle were identified as undetected. A pickup a pickup cycle detected with no true pickup gesture, ground truth gesture occurring within the cycle are false detection. We conducted trials to tuning the parameter of the algorithm and evaluate the sensitivity of our method of the detection. After the trials of investigation of the algorithm, we set the threshold value 1 at 15 and threshold value 2 at minus 15 and threshold value 3 as 0 for the cycle of the gesture detection. After computing the result, we found we the algorithm could help us to detect 202 pickup gesture out of 226 ground truth gesture. The resulting sensitivity of the device and the method is 98.38%. Then we calculate the load cell data from the true detected cycles. The sum of the positive load cell value data was calculated once the second if condition is satisfied in the algorithm 1 and the row angle data is within the threshold value of 15 and minus 15. Then we compute the average of the load cell value. We compute the Pearson correlation coefficient of the load cell value and the ground truth weight data. After further exclude the outlier from the dataset, we then get the R value at the 0.87, which shows a high correlation between these two values. The model was then trained based on the dataset using leave one intake out cross validation. We then compute the weight estimation accuracy by computing the mean absolute percent error. The result is 26.297%, which is relatively lower than compared with one previous work. And the mean absolute error was calculated to be 1.357. In our prototype is still bulky for most of users due to the size of it. Future iteration of smaller prototype are needed. There may potentially be different eating patterns while using various utensils, which could be explored in the future work. Our study didn't consider potential distraction events such as sharing a meal with other people and multitasking while eating and drinking. We know that everyone has their own eating patterns, and our method could not distinguish such individual pattern yet, but we could do such kind of thing in next phase of the project. We are interested in the result of a longitudinal study to validate our method. In the field studies such as data collection with the eaters in a university cafeteria will be fruitful to generalize the method in a larger scope. After we detect the food pickup gesture and the food's weight on the utensil, we could then potentially compute the eating rate. With the device that could provide eating rate detection, researchers could design various feedback mechanisms to intervene users' eating rate. We currently working on deploying the algorithm to the prototype itself, and we also work on improve the accuracy of the method in the future. In unhealthy eating behavior could trigger various health issues. This paper proposed a solution to help eaters monitoring their eating rate by detecting their food pickup gesture and calculate the food weight on each pickup. From this idea, we built a proof of concept prototype fork with various sensors. To the extent of our knowledge, this is the first solution to both calculate the food weight and detect the food pickup gesture with from a folk. We conducted an in-the-lab study to assess the efficiency of the method by examining the user participant data. In the future, we hope to leverage our funding of this project by deploying these features onto the next iteration of our prototype so that it could be used by real users in their own eating setting up. Thanks so much for attending my session. Uh, I think that's it.
Thank you, Zoe, for your talk and presentation. It was very nice. So we do have some question in the chat channel. So Anna was asking about how heavy is the frog prototype for now, and in terms of application, she's wondering if the weight of the forks with all the sensor and bait can affect the rate of eating.
So for now, the current solution is only focused on the detecting of the food pickup gesture and the amount in weight on the fork. And in the future, we could design some different. Actually, we are working on design novel feedback mechanism to use the detection capability to provide information to users to kind of help them to regulate their eating speed. And improve their eating habits.
Okay, thanks. Um,
Zoe?
Yeah.
Sandra, can I ask a question?
Yes.
Great. Hi, Zoe. Great presentations. I'm just curious about the range of stability that you can reach with such a prototype. Have you looked at the patient's profile to see what kind of profile you can reach with this technology? I mean, if you look at people with Parkinson's diseases versus people with cerebral palsy, you have a huge discrepancy difference between both profiles. So what's your profiles in terms of health applications? What user you are targeting? Can you just by that?
I think for now we are target for the potential users who want to monitor their eating speed and kind of reduce their eating speed if they eat too fast, or maybe remind on their eating speed if they eat too slow. And yes, I think your suggestion is a pretty good point to say that how we can leverage our current solution to broad more potential users, especially for some Asian people and patients in the hospital. But the thing that's it's probably tricky to say that to get such kind of participant to involved in our study. Yeah.
That could be future venue, probably. That sounds really interesting from both perspective, both nutrition and access to eating without talking the caregivers and family members. Thanks so much for this presentation.
Cool.
yes, thanks. I will do have like a final question for you, Zoe. Did you
Yeah.
think in the future work to use a spoon instead of a fork because the gesture is kind of the same? And I wonder if your algorithms right now may be able to extend your work on the fork on a spoon.
Yes, I think for now we focus on the folk because we found one paper saying that the folk user in a controlled study by some nutrition nu- nutrition researchers in states saying that the folk user in a controlled study eat less than spoon user, and yes, in potential that could be a potential studies to investigate the spoon users gesture and see whether we could detect their eating gesture and weight on their on the spoon. Thanks for your question.
Okay, thank you. And sorry, we do have another question from Colin. Just so I'm sorry about that. He asked, don't, don't you falsity the test if you tell the participant how to do it? I mean, they should not thinking of what normal eating speed.
Uh, as because we introduced the eating the study of the whole procedure uh, to the participant, saying that please use this fork to eat the fruit and as your speed that you feel as your normal eating speed and you feel comfortable, so that we try to uh, avoid either increase their eating speed or reduce their eating speed. But yes, I think that's a good point on the influence of our wording of the instructor to the participant on the final result. Yes, I think that's a good point.
Sandra, can I interact with that?
Yeah, sure, sure. Go ahead, Hamin.
Yes. So Zoe, basically, this is why I asked the question of looking at specific patients versus the well-being application, if I can call it this way. When you look at healthy people, the message, the neural message is transmitted from the brain to the hand so that you can eat at your own rhythm. However, when you look at people like Parkinson or cerebral palsy or some other pathologies, um, the message is here in the brain, but it will not be transmitted to the hand. There is this cue is not like the message is not understood by the neurotransmitters, so you cannot understand anyway. So when you look at patients, you will not fake this attitude. You will get them physical stability, like mechanical stabilities, without accessing to their, like without biasing their nervous system or supporting their nervous system. So that's why I looked at pathology versus well-being application. I'm calling that this way now. Yeah.
Okay. Thanks.
No worries. Thank you.
Okay, thank you again, Zoe, for your talk and your presentation.